Hi, this is Amarkumar Agrawal from Hyderabad. Today I will talk on Peter-Box scenario in extended symmetric teleparallel gravity. This was been done with the collaboration of Yulata Mishra and PK. In this work, we have reconstructed a Q model that can produce a solution for the stability nature of our model. We have studied through the scalar approach. This is the outline of my presentation. So I will start with an introduction. We will see why there is a need to study the bouncing solution of our universe. In the basic formalism of the field equation, f of q gravity. Then we will see the matter bound scenario in f of q gravity. Then using the conformal function, we will analyze the behavior of spectral index and tensor ratio. Then, through the dynamical system analysis, we study the different states of our universe. Then, we will see the stability nature of our model to the scalar condition. At the end, we will use the conclusion. As we all know, our universe is expanding and accelerated way. The rate of this expansion or along spatial direction can be obtained through the and the equation of the one, which is dependent a dot upon as we have seen that universe is expanding. If you go back in time, there must be either scale factor acquires a zero value, its singularity is, or it never acquires zero. It is a decreasing process, non-zero positive value, and again it is increasing, which leads to a bounce of our universe. It is suggested that this quantum theory of gravity may avoid this initial singularity issue, but we don't know what is the correct quantum theory of gravity. In the absence of fully accepted quantum theory of gravity, Bound's cosmology is the most promising one that allows us on singular. There are certain conditions that to be pulled in the bouncing cosmology at a bounce. The scale factor should not be zero. The first derivative of this scale factor with respect to cosmic time should be zero at a bounce, and the second derivative with respect to cosmic time should be positive. There are many work has been done in the many modified theory of gravity, uh, like FR, FRT, and many, but not that much work has been done in epoch period. Hence, the motivated from the loop quantum cosmology, we are going to study the matter-bound scenario for the epoch period. Now, the metric affine connection can be represented as equation 1, in which the Levi-Civita connection, co-torsion tensor, and the deformation tensor are represented in equation 2 respect. This full potential term is represented in equation 3, in which these non-metricity tensor are respectively represented after this superpotential terms. And the non-metricity scalar is represented in equation 4. Now the action equation for this epoch Q gravity is represented in equation 5. Now by varying this action with respect to metric tensor, one can easily get the field equation for this epoch Q gravity, and the energy momentum tensor for the matter content is represented in equation 7. Now we want to study this bouncing cosmology in FLRW spacetime. So that we have considered this line element which is represented in equation 8. For this line element, these field equations are represented in equation 9 and 10 respectively. As we have mentioned above, we are motivated from this loop quantum gravity in which the Hubble square term can be represented as equation 11. So that we want to get the same Hubble square term in epoch Q gravity. And the continuity equation and the energy density equation for the combinatorial case can be represented as equation 12. Now the matter energy and the Hubble parameter and the scale factor are respectively represented in equation 13. Now using this A folding parameter relation with our scale factor, we got Hubble square term as represented in equation 14 from equation 11. Now we want to get this FOQ model, which can produce the above Hubble spectrum. So that we have considered the two values, A as rho c upon 3 A naught cube and B as 1 upon A naught cube. And we know that this non-metricity scalar is 6h square. Using this relation, one can easily get this e-folding parameter, which is represented in equation 15. Now, we want to see the behavior of our model in the matter-dominated. In general, this energy density can be written as equation 16. But we have considered only matter-dominated case, so that we can see that for matter-dominated case, the EOS parameter becomes 0, and for that we got this FOQ model, which is represented in equation 17. This model can produce matter-bound evolution of our index. And we plotted this graph using above equation. In the left plot, we got this scale factor behavior with respect to cosmic time, in which we have analyzed that the scale factor is in contracting crosses non-zero positive value, and again it is expanding in the positive zone. While in the right hand side, we have plotted this graph for energy density with respect to Hubble parameter. We have seen that this Hubble parameter becomes 0 for minimum and maximum value of the energy density parameter. While on the other hand, while this energy density is increasing, this Hubble parameter shows a negative behavior, while the energy density is decreasing, Hubble parameter shows positive behavior. This negative Hubble parameter shows contracting phase of our universe, while the positive behavior of the Hubble parameter shows expanding behavior of our universe. Now, to study this slow roll parameter and uh, spectral index and the tensor to scalar ratio, we have considered this action equation for the scalar field, which is represented in equation 18. Now, the above equation mapped to scalar tensor action by applying this transformation, which is represented in equation 19. If the FOQ model spacetime is characterized by the FLRW matrix with a neta with conformal time, so that we can get this line element which is represented in equation 20. The line element is associated with the scalar tensor model, and matrix can be changed as equation 21. Here, suffix S denotes the scalar tensor frame for all fields. And the field equations for the scalar tensor frame, one can easily get as equation 22 and 20. Using this scalar field equation, one can easily get this equation 20. And here we are defining this row roll parameter in equation 25. The spectral index and the tensor to scalar ratio are defined in equation 26. Now, using this relation, one can easily get this conformal time equation, which is represented in equation 27. And we are also considering this conformal factor, so that we can produce this scale factor in FOQ frame. It is simple to see that the conformally connected FOQ frame is factor exhibits the following behavior of this scale factor in conformal time. While we are considering the approximation as neta is close to 0, one can easily get the scale factor as a 3 by 4 rho c t square plus 1 raised to power 1 by 3 in FOQ frame. Now, using this relation, one can easily get this spectral index, and in which this conformal factor, which is represented in equation 31. As we have noticed that for beta equal to 0.1 and nt equal to 16, the spectral index is consistent with the Planck region. Moreover, the scalar spectral index and the tensor to scalar ratio in the Planck tensor in the scalar tensor frame values are ns is equal to 0.9649 plus or minus 0.0042, and R is less than 0.064 respectively. And these are constraints with the Planck's 2018 results. Now, to study the different phases of our universe, we are going to study the dynamical system approach. For that, we are redefining our f of q model as q plus psi. For that, we are redefining our field equation as equation 32 and 33. The density parameter for matter, radiation, and dark energy phase are respectively denoted as omega m is equal to rho m upon 3h square, omega r as rho r upon 3h square, and omega te as rho te upon 3h square. As we know, the addition of these density parameters becomes 1. And also we are considering two-dimensional less variable as x and y, which are represented in equation 34. After doing some mathematical calculation, we are getting this two-dimensional system, which is represented in equation 35 and 36 respectively. From these two equations, we have plotted this phase space portrait, and we come to know that this matter dominated case we are getting the stable mode, and for the radiation dominated case we are getting unstable. Now, to study the stability of our model, we are considering the scalar perturbation approach, and the perturbation in the Hubble parameter is denoted by delta, and perturbation in the energy density parameter is denoted by delta H. The perturbation of the function f of q is represented as fq into delta q, and for this we are represented delta fq is equal to fqq into delta q. Neglecting a higher power of delta, one can write this equation for the non-metricity scalar, which is represented in equation 39. Subsequently, we are getting this relation between delta and delta m from the first field equation, which is represented in equation 40. Moreover, from this continuity equation, we are getting this relation, which is represented in equation 41. Here from 40 and 41, we are getting the first order differential equation, and after solving these, we are getting the value of delta m and delta, which are represented in equation 43 and 44 respectively. Now, in this figure, we have plotted this perturbation of delta with respect to cosmic time and delta m with respect to cosmic time. We have analyzed that it is showing increasing behavior in the early stage, while in the latter stage, it is going to zero and shows the stability nature of our universe. Conclusion. In this paper, we have studied this f of q model, and we produce one more model which can use as a bouncing solution. Through the conformal transformation, we have analyzed that the scalar spectral index and the tensor to scalar ratio in the scalar tensor frame are ns is equal to 0.9649 plus or minus 0.0042, and R is coming out to be 0.064 respectively, which consistent with the Planck's result 2018. Through the dynamical system analysis, we have analyzed that the matter-dominated case, universe shows stable behavior, while for the radiation-dominated case, universe shows unstable behavior. From the evolution of the perturbations of Hubble parameter and the energy density parameter in the cosmic time, they are approaching to zero at a late time, confirming the stability nature of our model in the most of the domains. Further study can be carried out on the reconstructed model f of q, which may give some more result on the bound scenario. Thank you.